This lab involves the casting and preparation of 3 samples of tin solder for hardness tests using a Phase 2 micro Vickers hardness tester. This video will provide an outline of the procedure and a brief description of the principles involved in the casting and hardness testing of the samples. In this lab, 3 tin samples are created using a die cast in 2 thermaline furnaces. In order for casting to take place, these 2 furnaces must be heated to 190 and 286 degrees Celsius. A die is assembled for casting and placed in the furnace being held at 190 degrees. The die used in this experiment is made of steel, and areas where tin will be poured into the die are lubricated with carbon, which serves as a releasing agent. Chunks of tin solder are placed in a crucible and carefully tonged into the furnace held at 286 degrees. The tin melts at this temperature, and when the tin fully melts, the die is removed from its furnace and the crucible with the molten tin is tonged out of the furnace. The molten tin is carefully poured into the crucible. This is done 3 times, and after pouring, the first sample is air-cooled, the second sample is quenched in water, and the third is furnace-cooled. After cooling, samples are ready to be hardness tested.
We used the Vickers hardness test to test the hardness of 3 tin solder samples that underwent different cooling conditions. Theoretically, the quenched sample is the hardest because grains have less time to grow and the resultant material will have a high dislocation density. This high dislocation density corresponds to a higher hardness. The furnace-cooled sample is the softest because the grains have more time to grow. A material with large grains will exhibit greater ductility because its dislocation density is lower and the motion of any dislocation is easier. The room-cooled sample will have a hardness somewhere between the quenched and furnace-cooled sample. While the rate of cooling is quick, grains will have a chance to grow but not greatly reduce the hardness.
The first step while using the Vickers hardness test is to place the sample on the sample stage. After that, check that the diamond indenter is locked into place and not the objective lens. Press the start button and wait for the sample stage to finish lowering from the indenter. Afterward, lock the objective lens and align the parallel lens visible when looking through the lens with the fourth side of the pyramid indentation. The dialers to the right of the eyepiece correspond to the penetration depth and must be input by using the number pad at the base. Once the numbers are input, the machine calculates the hardness. The Vickers test is invaluable to material scientists. From hardness data, we can extrapolate important information as to grain size and, in turn, dislocation density.